Okay, Lenny.
So today we're happy to have Azadeh Maleknejad. I hope I didn't pronounce that too badly. And she's a Royal Society University Research Fellow, which is a very, very prestigious fellowship. And she's currently at the University of Swansea. And she has done a lot of work on theoretical cosmology and QFT. So I think this is a slightly different direction that we're taking today at the SCONE talks, but I think it fits in the general semi-classical paradigm where we're trying to have more talks on. So let's start. Azadeh, the floor is yours.
Thank you very much, Elena, for the nice introduction, and the organizers for the invitation. It's a great pleasure to be here with you today for another SCONE seminar, if I pronounce it correctly. As you may see on the screen, it's gonna be more in the cosmos side. So I will start with a brief recap of what we already know about the early universe, and I hope we can make it as interactive as possible. So please interrupt me with any questions that you might have. In this talk, I'm going to tell you about Fermion creation by cosmic perturbation at one loop. It's a work in collaboration with Joachim Kupp at CERN. It's a topic that I'm very excited about, and I hope by the end of this talk I can share some of these excitements with you. Behind this fancy word, what I'm really going to tell you about is a possible connection between geometrical radiation in the space-time, the so-called gravitational waves, and the matter production in cosmology. And it's a new gravitational mechanism for matter production in the universe. So the story behind this story was some theoretical curiosity that we have with my collaborator. We were looking for effects that are exactly zero at tree level in expanding universe, meaning FLRW geometry, because they are protected by a symmetry, and in particular conformal symmetry, but they are non-zero at one loop when you turn on cosmic perturbations. Interestingly, not only we found such effects, but also we realized that they have interesting phenomenological consequences for cosmology, because that leads to a new gravitational mechanism for matter production in the early universe. So as you know, the matter content of our universe is 68% dark energy, this mysterious form of energy. And then only 5% of that is made of atoms, which are the standard model of particle physics. Since we know the matter content of this 5% is kind of sort of, you may think, okay, we understood 5% of the universe, but that's not entirely correct, because even for that 5%, you still need to explain the matter-antimatter asymmetry that we observe today, and that requires a source of CP violation beyond the standard model. Then we come to the dark matter, which is almost 1/3 of the whole matter content. But here the situation is even worse, because not only we don't know how dark matter got generated in the early universe, we don't even know the particle nature of that. So among the common puzzles of the standard model in cosmology are the particle nature of dark matter, the origin of the matter asymmetry, and how dark matter has been produced. So I called the last two puzzles the matter creation puzzle, and we often assume new physics interactions to answer this question. But what about gravitational fields? So the question that I'm going to explore in this talk, because gravity is universally coupled to matter and is unavoidable. And so the question is how far gravity can contribute to matter production in the universe. I divided this talk into three main parts. The first part is about quantum fluctuations in cosmology. Then I will talk about gravitational particle production. And finally, I will tell you about gravitational wave background, this geometrical radiation, and its possible connection to matter production. And this part is divided into two parts. In the first part is about polarized gravitational waves when in the early universe, the physics could tell between left and right. And the second part is about unpolarized gravitational waves when parity is the symmetry of the early universe. Good, so now let's turn on quantum fluctuations in cosmology. Thanks to Heisenberg's uncertainty principle, of course, quantum vacuum is not empty, but this vast ocean made of virtual particles getting generated and annihilated in a fraction of a second later. But on the average, still we have nothing. However, if we have a background field and this background is strong enough, it can upgrade these virtual particles and turn them into actual particles and leads to a particle production mechanism. Some of the famous examples of this background effects are as follows. Perhaps the most famous one is Schwinger effect when in the presence of a constant electric field, if this electric field is strong enough so that the work of the Lorentz force of the electric field over the quantum wavelengths of the pairs of charged particles is at least equal to the rest energy of charged particle, then it can produce them. And to have a feeling about the size of this electric field that you need to produce particles, of course, we can consider the lightest charged particle of the standard model, the electrons, and then we see that we need an electric field at least equal to 10 to 18 volt per meter, which is huge. And up to now, we have not detected this effect on Earth. However, of course, the energy scales in the very early universe are very high, and in principle, they can be the highest energy scales observable to us. So it's very natural to look for this effect in the early universe. And interestingly, and in the context of axion inflation, this can naturally happen and comes with some observable effects. That's a mechanism that we found with my collaborator, Lozanov and Komatsu, and it leads to a new avenue of research since then. If you are interested, you can take a look at this Nature Review Physics that covers several related mechanisms. Good. The next example, which is based on a gravitational background, is of course the Hawking radiation. And that's when in the presence of the event horizon of a black hole, if a pair of virtual particles actually happen right at the event horizon, the one which is slightly inside the horizon will fall into the black hole while the other one escapes. And that's how Hawking radiation can lead to particle production and black hole evaporation. Finally, we get to another example of background gravitational field that can lead to particle production, and that's the expansion of the universe. In this case, so in flat space, you start from vacuum, you have a pair of virtual particles, but then in a fraction of a second later, they find each other again annihilated, and you have still nothing. In an expanding universe, however, you start from vacuum, and then you have a pair of virtual particles. And In case the expansion of the universe underlying them is fast enough, then this pair cannot find each other. And as a result, the expansion of the universe leads to particle production. And that's an intuitive way to understand this process. The first person who actually discovered this effect was Schrödinger himself, but he wasn't really comfortable with his own discovery, and he called it an alarming phenomenon. 85 years later, nowadays, it seems like that's exactly what happened in the very early universe, meaning that we believe that the expansion of the universe during inflation stretched these initial quantum fluctuations, turned them into actual cosmic perturbations. We call them primordial cosmic perturbations. And then by cosmic evolution, they evolved and imprinted on CMB to form the CMB anisotropies that we observe today. And finally, they got imprinted on a matter field and formed the larger scale structures that we measured. So in a way, ultimately, we are the product of quantum fluctuations in the very early universe. The first person who actually parameterized systematically this cosmological gravitational particle production was Parker. He was the first who systematically developed a theory of gravitational particle production in an expanding universe using QFT in curved spacetime. So basically, of course, because of the expansion of the universe, the initial vacuum is not the same as the final vacuum, and it leads to particle production. But conformal fields in 4D will not be produced since FLRW is conformally flat. So basically, Parker formulated the cosmological gravitational particle production, but he also realized that there is a part of fields that cannot be produced by this mechanism. Is there some of us would be really grateful if you can kind of upload the videos of it?
No, it's not a question. It's for organizers, actually. Sorry for the slides. No, ma'am.
Sorry. Are there any questions, by the way? No? Okay. Good.
So maybe I can ask a quick running question. So like, if I understand for Hawking radiation, like the event horizon is needed. For example, same for de Sitter, etc., or the rain blood. But if it is a flat FLRW, there is no horizon to begin with, right? So how do you even expect the particle production? Like, in a sense that, I mean, if I go by the entropy, you need some horizon to cut off the information. Like, I mean, how can a non-horizon space-time can give rise to entropy? Like, probably a very naive question, but just asking.
No, actually, that's a very good question. So the detailed answer requires some time. Let me see if I can give you a quick answer. So in particular, what I'm talking about here is mainly particle production during inflation. In this case,
yeah, for de Sitter space, you will always get particle creation production. De Sitter, I understand, but I am asking that you are probably extending into FLRW metric, right? When in the next slide. So that's what I am a little confused, because FLRW doesn't have a horizon, right?
So it's a little bit different. It's not exactly about the horizon. So I'm mainly interested in the following slides when I mentioned the conventional mechanism. I'm interested in a case when this particle production happened at the very last e-folds of inflation, but you don't really need that because this is different that the horizon discussions that actually it's different at the Hawking radiation. Basically, so here because the time translation is broken by the expansion of the universe. You always have the mixing between positive frequency and negative frequency modes, and this mixing leads to particle production. So it has they are both gravitational, but so the source of this particle production is different. Maybe if I go to the next section,
Sure,
it gets
sure,
more clear. Yeah, but thank you for the question.
Sure, thank you.
Are there any more questions? Okay, good. So I forgot how to go to the next. Good. So related to your question, maybe this slide can clarify. Consider a scalar field in an expanding universe, and here I'm talking about a normal scalar field minimally coupled to gravity. Okay, it's a massive field, and we put that in the cosmological background, and this is the field equation, the Klein-Gordon equation in a Fourier space with this effective frequency squared. Interestingly, you see that even if I set m to 0, still the effective frequency squared of the scalar field can feel the expansion of the universe. This R here is a Ricci scalar, so it's proportional to h squared. So interestingly, this scalar field can get generated by the expansion of the universe deep in the UV. You have a normal QFT in flat space. So this is how you define your vacuum by Bunch-Davis vacuum. But when you go to the IR, and in case that this term dominates, then you have a different vacuum states. And as a result, that leads to particle production. I hope that clarifies, but if not, we can discuss at the end of the talk. So here we have the number density of this scalar field produced by the expansion of the universe in terms of the momentum here, HE, and is basically the Hubble at the end of inflation. You see that by decreasing the mass of the scalar field, you're actually increasing the particle production. And that's an example of cosmological gravitational particle production. Are there any questions? Okay. Now let us put different spinning fields in the cosmological background and see what happens. You see that for the scalar field, like the normal scalar field, minimally coupled scalar field, and a spin 2 field, and also for the vector fields, the longitudinal mode, you have, so here we have the number density rescaled over h cubed, and here we have a mass over HE, which is the Hubble at the end of inflation. You see that by decreasing the mass of this particle, you're actually increasing the particle production by the expansion of the universe. However, there's another kind of particles, spinors, conformal scalar fields, and the transverse vector fields, that by decreasing the mass of the field, you're actually decreasing the particle production. So these two kinds of fields have different behaviors related to the expansion of the universe. And this is just a consequence of Parker's conclusion that conformal fields in FLRW will not be produced since FLRW is conformally flat. And basically, when we get to massless limit, these fields are CFTs. And just to have a feeling how come this actually happened at the level of field equation, let us take a look at spin half massless fermion. So here we have the Dirac action, and d mu is the spinor covariant derivative in terms of the spin connection. Again, we put it in the cosmological background. And this is the field equation of the fermions. Interestingly, you see that all the effects of the expansion of the universe now just appear in terms of h. H is the Hubble parameter, h dot over a. And so apart from this, everything else is just a flat space fermions. Interestingly, by absorbing that and with this conformal factor in terms of the scale factor, you can find a field equation for the fermion that actually lives in flat space. Interestingly, this new field is the canonically normalized field of the fermion. In cosmology, we use this, the canonically normalized field, and that's the one that its initial condition is set by Bunch-Davis vacuum. And as a result, the physical fermions in cosmology, they live in flat space. They don't feel the expansion of the universe. And that's why for the fermions, as you go to massless limit, you actually don't have particle production because they don't feel the expansion unless they have a mass. Are there any questions so far? No. Good. So how to create fermions then in an expanded universe? Of course, you need to break the conformal symmetry of these wild fermions by interactions. And what I mean is more precisely the dilatation transformation of the wild fermions. So in order to break that, you need to couple them with some extra fields. It can be just something beyond the standard model, like the infotron field, the standard model, new interactions, dark sector coupled to thermal baths, or you just make them massive. And if they are very massive, they can get generated gravitationally by the conventional mechanism. But is it the best gravity can do to produce fermions? The answer is no. And that leads me to the second part of this talk, which is gravitational particle production mechanisms. And in the following, we will consider some sectors beyond the standard model that are just, so this sector is just gravitationally coupled to the standard model. And by gravity, I mean Einstein gravity. And here we have a summary of different gravitational mechanisms for particle production. The first one is, of course, the conventional one, cosmological gravitational particle productions that we discussed based on the expansion of the universe. That can be effective for dark matter production if the mass of these particles are very heavy and typically more than 10 to 13 GeV. And then this is the formula for the energy density of these fermions produced by the cosmological gravitational particle production. The second mechanism is graviton-mediated annihilation when you have some off-shell gravitons in a very hot early universe plasma, typically with temperatures higher than around 10 to 13 GeV. Then in this very hot soup of particles, which is full of standard model particles or some other intermediate particles, they can gravitationally annihilate to this heavy dark sector and contribute to dark matter production. And in this case, the energy density of these fermions is related to the temperature of the plasma and their mass as this formula. But how about cosmic perturbations? The point is that the whole point was that based on the Parker's conclusion, you cannot produce massless fermions if in FLRW geometry because of the conformal flatness of this metric. But cosmic perturbations can naturally break this conformal symmetry, and they are unavoidable. We actually measured them and CMB fluctuations and also in larger scale structures. So they can definitely break this conformal symmetry of massless fermions. So how far they can contribute to this matter production. And that leads to this other two mechanisms. The first one is via the gravitational ABG anomaly, when you have chiral gravitational waves. And in that case, you can produce chiral fermions if you have a source of parity violation in the early universe. And the other one is this final mechanism that we call it gravitational wave-induced freeze-in, when even for unpolarized gravitational waves, this cosmic perturbations, this background of gravitational waves can produce massless fermions. Let us first take a look at gravitational ABG anomaly. The global gravitational anomaly relates, this prefactor should be, it's more than 16 pi squared, sorry. It relates the axial current of these massless fermions to the RR tilde, which is the gravitational Chern-Simons in the presence of chiral gravitational waves. And by RR tilde, I simply mean R mu nu lambda sigma R tilde mu nu, that is wrong. Alpha beta beta. Sorry, it's anti-symmetric over the first two indices, if that's clear. No, let's write it like this. You know, sigma lambda epsilon sigma lambda. So basically, I mean this by RR tilde. Good. So in order to have a, so then the question is how to have a non-zero RR tilde. What makes this chiral gravitational waves? To generate circularly polarized gravitational waves, you need a source of parity violation in early universe or in inflation, for example, that is a source of, that can distinguish between left and right, or the two different helicity states. That can be done by different mechanisms. And the first one is actually by a modified gravity interaction, a Chern-Simons gravity, and you have an axion, a pseudoscalar inflaton field that is coupled to this RR tilde. Or you can have some non-abelian gauge fields coupled to some axion inflation. And then you have an effective action like phi FF tilde. And interestingly, this will also source gravitational waves and provides chiral gravity waves. Interestingly, this mechanism, so you start from chiral gauge field, and then that leads to chiral gravitational waves. Interestingly, this is more efficient than the normal just modified gravity interaction. And you can see that all the Sakharov conditions are satisfied in axial inflations if you couple them with the non-abelian gauge fields. And that can lead to an efficient way to produce leptogenesis during inflation. Unfortunately, that doesn't work for U1 gauge fields. Now, are there any questions so far? No? Good. So now let us take a consider a phenomenological model for omega gravitational waves. And so up to here, I just told you about a source of chiral gravitational waves during inflation. But what about later on during reheating or afterward? Let us consider a phenomenological model for omega gravitational wave, which is chiral, like when you have a circularly polarized gravitational waves. As the simplest spectrum, let us consider a broken Pavel law spectrum with this structure. And so here, basically, I have a broken Pavel law omega gravitational wave today. When this omega peak is simply this peak here. And this is the total spectrum. I can break it into chiral pieces for the left-handed and right-handed helicity states of graviton. Then I can write it like this. So this omega gravitational wave 0 is the spectrum of gravitational wave measured today. We can consider that it is chiral today, and you can parameterize that in terms of this chi q. But it's not all the parameters. There is another factor related to time evolution of gravitational waves. So here, this is the gravitational wave with helicity state S that can be plus or minus. In terms of time, you have 1/a, which is the redshift of gravitational wave due to the expansion of the universe. You have some evolution function, and then you have the oscillations of the wave and its value today. This evolution function can also be polarized, meaning that during the production of gravitational waves, the left-handed and the right-handed modes can evolve differently. So they both start from 0, but one of them can grow faster comparing to the other, or have a different value of beta. So that can be modeled by adding this extra factor of b chi. So now in total, we have 2 factors, chi and b, that can parameterize the chirality of gravitational wave. Interestingly, even if I set chi to 0, so that the gravitational wave that we measure today is unpolarized, still this b is a factor of polarization. So you start from some chiral evolution for gravitational waves, but it ended up to be washed out eventually. So this is how, or they can both be non-zero. That depends on the different scenario that you have. Now let's put that spectrum to calculate the gravitational ABG anomaly in the presence of that gravitational wave background. So here we have the energy density of gravitational wave, which is this broken spectrum in terms of momentum. And then in dashed line, we have the fermion number density produced by this gravitational wave, which is which has the same structure. And then it's parameterized also in terms of this curly NP, which is basically somehow the amplitude of this spectrum. And interestingly, here we see that even if I set chi q to 0, meaning that the gravitational wave spectrum today is unpolarized, still the fact that this gravitational wave can, for a short time, be chiral is memorized in the fermionic sector. So in a way, it's related to Atiyah-Singer theorem that somehow the chirality in the gravitational sector is memorized in the fermionic sector. And now, throughout cosmic evolution, you can actually study the energy density of these fermions rescaled by the energy density of gravitational waves. During the generation, you have a source that can produce these gravitational waves. So and then the same gravitational waves sourced fermions, and then in red you have the evolution of this ratio increasing with time. Then after the end of this transient phase, gravitational waves are now fixed and just doing a redshift acting like radiation, and these fermions, until they are massless, they would follow the same evolution, so this ratio would be fixed. But then eventually the fermions will get their mass, and then this ratio increases like the scale factor. And of course, as you increase the mass of these fermions, you're increasing this ratio. Are there any questions so far? No? Okay, so here we want to see what is the consequence of the gravitational ABG for dark matter production. In this plot, we have...
So maybe just a quick running question.
Sure, yes.
Oh, sorry, there is a lag probably because of my internet connection. So I'm just asking that maybe eventually you want it to be scale invariant spectrum. Like, don't you want n to be, let's say, 4, like the Zeldovich spectrum, because the current one, like the post one, is the Zeldovich spectrum, right? So it is like the post gravitational one. Yeah, like when it is re-entering the horizon, then shouldn't you want to fix to be n to be, say, 4, like the scale invariant power spectrum? Like power spectrum is fine, but I mean, eventually it saturates to Zeldovich spectrum, like, so that's what I was just wondering.
Good. So here in this part, I'm not talking about in this section. Good. So this part was about inflation, and that's related to your question, when the modes actually leave the horizon. In this part, we're talking about gravitational waves during radiation era, or like afterwards. So these modes will never leave the horizon. And this analysis is actually inside the horizon. And this is a typical spectrum for gravitational waves from preheating, reheating, phase transition, and so on.
I see. So it is in the sub-Hubble horizon limit, right?
Exactly. So this mode, there's a cut here, which is the cosmic horizon. So this is a different story. But in the previous slide, when we talked about inflation, then your question is related to this part.
Okay, thank you very much.
Yes. Are there any more questions? Okay. So here we have the temperature during which these gravitational waves are produced, and then we have the mass of the fermions, the final mass. Since in this story, I assume that these fermions are massless during generation, then basically this gray shaded area is not accessible for me. But before looking at the prediction of gravitational ABG anomaly, let us see what is the prediction of the conventional mechanisms. This is the standard cosmological gravitational particle production if these fermions were initially massive to begin with, and you can produce them just by the expansion of the universe and forget about the cosmic evolution, the cosmic perturbations, in this case, gravitational waves. If you turn off all the cosmic perturbations. Here is the prediction of the scenario. In yellow shaded area, the solid line shows the parameter space when the cosmological gravitational particle production produce all the dark matter today, and then the dashed line here in yellow shows the part of the parameter space in which this mechanism only produce 1% of the dark matter. And then here in this part, we have the graviton-mediated annihilation era when you have off-shell graviton. So here we're not talking about cosmic perturbations. We're talking about the second mechanism that I showed you in that table. And in that case, you also need your fermions to be massive. And this is the parameter space that mechanism can produce dark matter. Now, let us consider the case that these fermions are massless during their production, and we want to look at the prediction of gravitational ABG on dark matter production. And it's a little bit depends on the parameters, but we have for different values of A reheating comparing to A star, that's the end of this production mechanism, then you get different values. And in red and in green, we have two typical values. You see this is when this mechanism can produce dark matter today. And you see that this mechanism, this gravitational ABG mechanism, can produce dark matter in part of the parameter space, which is not accessible for the conventional mechanisms. You can use exactly the same setup to produce the standard model leptons and baryons, and this is the so-called gravitational ABG leptogenesis. But this is more fine-tuned, since in this case, in the dark matter case, of course, the mass of the dark matter is unknown. So I can consider that as a free parameter. And so that means that I have a broader accessible parameter space. But when I'm talking about leptogenesis and baryogenesis, then the mass of these particles are fixed. And in that case, in order for this mechanism to produce all the standard model particles, then the reheat temperature should be as high as 10 to 14 GeV, with omega peak of gravitational waves to be 10 to -6. So these two will, in 10 years from now, will be probed by future measurements. So basically 10 years from now, it will either be able to rule out gravitational ABG leptogenesis, or it can have a hint for that. Then we get, so now that we saw that polarized gravitational waves can produce fields, particles, matter fields. What about unpolarized gravitational waves? Unfortunately, I did poorly with time. Hopefully, I can finish this part. So for unpolarized gravitational waves, this is a mechanism that we call gravitational wave freeze-in. In that case, in a nutshell, it's the stochastic production of fermions by cosmic perturbations. Here, we assume a broken parallelized spectrum for gravitational waves, but this time unpolarized. So we don't need a source of parity violation. And we are in radiation era, so we're not talking about inflation. Interestingly, you see that for these conditions, none of the previously discussed mechanisms can actually produce these fermions. Because they are massless, they cannot be, they are massless fermions, they cannot get generated by cosmological gravitational particle production. Since we don't consider a hot plasma with massive particles, graviton-mediated annihilation mechanism also doesn't work. There is no source of parity violation, so R tilde is also 0, and gravitational ABG vanishes. So the only possible mechanism is this one that we're gonna discuss here. So we have fermions in an expanding universe, and unlike the previous case, now we have gravitational waves, we have cosmic perturbations in the metric. Of course, the wild fermions can't feel the expansion of the universe, they don't couple to the FLRW geometry, but they can feel cosmic perturbations since they are coupled to gravitational waves with this cubic and quartic interactions. And then you can calculate the energy density of these fermions produced by this classical stochastic gravitational wave background using the in formalism. When you sandwich your operator with this unitary operator U in terms of the interaction Hamiltonian H interaction, which is related to this Lagrangian densities that we showed in this part. Long story short, let's just consider this broken Pavlov spectrum and calculate the energy density. The final formula is like this. You have the unequal in time power spectrum of gravitational waves, and that is a stochastic expectation value. It's not a quantum expectation value. And then this part is basically just a quantum fermion field. So this part is the expectation value of the quantum field, but this part is a stochastic gravitational wave. So that in a way, it's a mix of quantum and a classical interaction. And this contribution acts like radiation, because if you calculate the pressure coming from the same process, the pressure is simply 1/3 of the energy. Now, to calculate this quantity, you need to also know the degree of temporal coherency of gravitational wave background. And of course, if you do some simulations, you have all the details. But here we were interested in doing analytical computation. So we consider the two extreme limits of the coherency of the field. So we will consider the fully incoherent and the fully coherent limits of the gravitational wave background. And doing so, you get the final energy density of the fermions given like this. So parametrically, it's proportional to Q peak to the 4, and Q peak is the scale that breaks the conformal symmetry of the space-time. And that's the peak of the spectrum of gravitational waves. It's also related to the redshift at the end of the gravitational wave production, and of course the energy density of gravitational waves at the peak. So up to the point, so here we have, I'm very close to finish. I only have 2 slides. So this is the energy of the energy of the universe. At T star, you have your effective massless fermions, during which the gravitational waves are produced, and also these fermions are produced by gravitational waves, and they are massless. at some lower temperature, these fermions get their mass, or they were initially massive, but their mass were much lower than a Hubble and T star, so you can neglect them. And eventually, when temperature gets below M, these are effectively non-relativistic, and you can calculate their final energy density, which is now proportional to also to the mass of these fermions. Then you can probe the parameter space accessible for this scenario. It's similar to the previous plots that I showed you. Here we have the fermion mass, and the horizontal axis shows the temperature at the end of the production of gravitational waves in dashed yellow, it's shaded yellow. Here we have the predictions of the conventional cosmological gravitational particle production by the expansion of the universe, no cosmological perturbations. Here is the prediction of the graviton-mediated annihilation mechanisms when gravitons are off shell, and again, no cosmological perturbations. And then in this colorful areas, we have the prediction of this mechanism. And again, I have to remind you that in this mechanism, we assume that these fermions are massless during generation. So this gray part is not accessible for us. Interestingly, you see that there are part of the parameter space that is not accessible for the conventional mechanisms, but is possible for this mechanism by cosmic perturbation to produce dark matter. And of course, you can consider different part of the parameter space to probe the accessible parameter space to produce all the dark matter today by this mechanism. Finally, this is my last slide. Sorry for going over time. Just like the electromagnetic field, gravitational waves have their own spectrum, the so-called gravitational rainbow. You can start from gravitational waves with frequencies as low as around 10 to minus 17 hertz, and these are wavelengths as large as the whole universe. You can probe them by CME measurements, and finally you get to a bit lower wavelengths with frequencies around nanohertz, and here you can probe them with astrophysical probes. Eventually you get to the area that will be probed by laser interferometers between 10 to minus 6 hertz to around 10 to 4 hertz. And finally, you get to higher frequencies when these gravitational waves are much more, that they have frequencies much larger than 10 to 4 hertz, and then you need new ideas to look for them. The gravitational wave frequencies that we need for this mechanism needs to be between kilohertz to gigahertz. So part of them can be probed by future generation of laser interferometers on Earth, like Einstein telescope. And then the other part needs new techniques to be probed by, but it's a hot topic of research. So with that, I finish this talk. I hope I could convince you that gravity and quantum effects in cosmology can still surprise us. And we discussed an effect that is zero at tree level in cosmological background in FLRW geometry, but they are non-zero at one loop in cosmic perturbations. And cosmic perturbations like primordial gravitational waves naturally break the conformal symmetry of wild fermions in cosmology, and it leads to a new mechanism for dark matter production and baryogenesis, leptogenesis in the early universe. Thank you very much.
Okay, so for the nice talk. Okay.
Yeah, you should come visit us at Swansea.
Oh, yeah, of course.
And I have ocean next in the window next to me.
Great, yes, of course. Okay, there were questions before, but I think that we can start the question sessions from the audience. So if there are curiosities or questions for the speaker, please. Yes?
Yeah, ma'am. First of all, thank you for this amazing talk. I mean, like, yeah, it's really amazing. So, but I have a maybe fundamental question. So, when you went to the fermions, in the Cole's paper, when you were talking that when the spinors you are coupling with the gravitational field, you said that the massless one, I mean, doesn't produces the particle production. Like, I mean, you probably commented something like that. For the fermions, you probably commented that the massless fermionic fields doesn't create the particle production, like if in the early slides.
Yeah.
Yeah. So I'm just asking, like, I didn't do it. I only know, say, the scalar fields in black holes and de Sitter space. So I'm just asking that, is there a physically intuitive way to get it? Like, I was thinking that if I take the spinors and like I do the Hadaman states as like splitting the two spinors, I mean, is it natural to expect that why massless should not create the particle, because the helicity and chirality both are same, like in a sense that chirality would commute with Bogoliubov transformation, so it doesn't happen. So it is probably a very naive question, but I just wanted to ask, like, is there a more fundamental reason that why massless Dirac fields doesn't create particle production? Is it because like the chirality matrix commutes with Bogoliubov transformation or something like that? I mean, it's probably a very naive question. Maybe it follows from some detailed calculation, but I was just quickly wondering.
Actually, that's not a naive question. That's a very good question. Thank you for bringing that to the discussion. Good. So Parker showed that if you start from the trace anomaly of the massless fermions, or also the conformally coupled scalar field, and then from that, if you calculate the energy density of these particles produced just by the expansion of the universe, so forget about cosmic perturbations, then you get zero. So that's the answer. But perhaps a fundamental reason for that is because since you mentioned the case of the black holes, in case of the black holes, you can also produce particles and can relate that to the non-zero Weyl tensor, because Weyl tensor squared is not zero, for example, in a Kerr black hole. In FLRW geometry, it's conformally flat, so the Weyl tensor is zero. And that's the reason. But the cosmic perturbations leads to a non-zero Weyl tensor, right? That's separate the two. Did I answer your question? That you have to do the calculations by yourself to get convinced that it's actually
Yeah. Thank you very much. I see. And it is always known that, I mean, like at the first loop, the conformal invariance always breaks. Like, I mean, the conformal anomaly always appears in the first loop itself, right? It is generally true for any field coupling. Like, I know that for the graviton interaction, there is a conformal anomaly, but I am asking that if graviton is coupling to Dirac spinor or something like that, does the anomaly gets cancelled, or like is it in general also true, like always in the first loop?
Well, I'm not sure if I get your question, but if your question is about the massless fermions are not unique, and you can ask the same question for Yang-Mills theory in 4D, which also have the conformal symmetry, and also the conformally coupled scalar field, they all can get generated and one loop in cosmic perturbations. But if you have a field that is not a CFT, then basically you can produce them more efficiently by just a conventional expansion of the universe.
Okay, thank you very much, ma'am. Nice talk.
And thank you for your question. Yes.
Okay, I think we have time to more questions if I have a curiosity for the speaker, but I prefer to wait for other questions first. Okay, I don't see any other questions, so I can ask you a very naive question. Sorry, because I'm not familiar with particle productions for fermions in cosmology. So sorry for in advance. But
No, but the
yeah.
whole point is to ask questions, is big fun. Yeah, I'm surprised that the previous I forget me if I'm mispronouncing your name, Sayantan. You're asking very good questions, and then you're starting
Yeah,
with,
good.
oh, I have a very naive question. It's not a naive question. These are all
Yeah,
excellent
okay.
questions.
Great. No. I mean, my curiosity was related about the computation when you essentially take the expectation value of essentially RR tilde, let's say.
Yes.
So, I mean, since you are in conformal couple case, you essentially are making a computation in Minkowski essentially. So your expectation value is with respect to the vacuum essentially of your. I mean, if I understood correctly, so.
Which part? This part?
Sorry, when you are computing the divergence of J of the current of the
Okay,
current.
good. So let's see.
I
This
cannot
one.
remember the number. Oh, yes, this one is essentially. So when you compute the expectation value of RR tilde, essentially, yeah, I mean, I figure out that you are using something like the vacuum, the Minkowski vacuum, since you are in a conformally coupled case, essentially. So
Yes,
this is
good.
correct.
So the way that we calculate, thank you very much for the question. So the way we calculate it, of course, I sandwich it between, because it's cosmology, and so I will sandwich everything with initial vacuum, right? And then I'm gonna calculate this quantity RR tilde at the leading order in gravitational waves. This quantity is that clear what I'm writing? I forgot my
Yeah, of course.
tablet
No,
as
don't
usual.
worry.
Yeah, so
Yeah.
the way that you do it is basically dk cubed up to some factors, and then there is a sum over polarization, which is plus and minus. Then you have, good, and then also there is a partial t. So for example, so this is, maybe it's better if I write it like this. Left dot squared minus k squared. By k squared, I simply mean this guy.
Yeah.
Squared.
Yes.
So it's HL squared minus, you have to switch left to right. Good. So this is roughly the quantity that you calculate. And interestingly, first of all, in order to have this quantity to be non-zero, of course, you need a source of parity violation. And so I'm doing these calculations in FLRW geometry. It's not flat space. And that's why I label things with O in, because it's the vacuum is dynamical and it's time dependent. It looks scary, but it's not. If you do the calculation, you will see it's straightforward. But basically, what I'm doing is calculating this mode in FLRW geometry and then put it in this integral. The fact that this RR tilde is parity violating means that you need a source of the source that produce HL, which is different than HR, to a source that can distinguish between left and right, and also your mode cannot act like a wave, because it does act like a wave, then this is zero and this is also zero. But that's basically how we do it.
Okay, I see. Thanks. Okay. Oh, sorry, just very, very, naive comment. I mean, is there a way, let's say, or have you planned to try to generalize this computation to massive fermions? Since, I mean, let's say when you're starting from something that is the conformal invariant, so the computation should be start to be more complicated, let's say. So I mean, I was wondering if I mean there is if you have I mean a way to try to address that problem also. That sounds more difficult in that sense, even because starting from starting from the fact that, for instance, the computation, I mean, for the in vacuum, let's say, should change because we have a mass and so on.
Good. So you're asking, now consider massive fermions. Of course, if I have a massive fermion, then I have the normal, this effect, the cosmological gravitational particle production, plus this n that produced by the cosmic perturbations, right? We have two parts. This part is actually prop this area, and this part, for example, okay, so this is the gravitational ABG. Your question is about this other mechanism or this?
It's about if you start, I mean, if you start with a background field, I mean, a matter field that has got a mass, so it isn't a Weyl-like field, let's say. So
yeah, so if all you need to do is to assume a field which where its mass is much lighter than the other parameters.
Okay.
During the generation of gravitational wave that is fermion production is actually happening. So then you can use our calculations, and then basically now you have two contributions. Also,
I see.
This one, and then you need to see which one is larger. So, for example, if you are in this area, so for example, if you are here, basically the conventional mechanism dominates over this effect. If you are here, then this mechanism dominates over the conventional mechanism.
I see. Okay. Oh, thanks a lot.
Thanks for the question.
Thanks. Okay, so let's wait for other questions from the audience, if present, for a while.
There's something in the chat.
In the chat, maybe. Oh, I think.
Okay,
Benito is already. Yes, Benito has already answered. Great. Okay. No, I don't think that there are other questions, so I think we can thank the speaker again for the very nice talk. And I mean.
And thank you very much for the invitation. I really enjoy your company, and thanks for having me.
Thank you, Azadeh.
Thank you.
Thanks for this nice talk.
Thank you for coming.
Thank you.
Okay, so I think that we can stop.